Good day to all of you. In today's lecture, we will continue with a few more problems relating to the steady state solution of power converters. We will look at a few power converters which are isolated power converters as well as non-isolated power converters, continuous conduction as well as in discontinuous conduction, and we will analyze these circuits to find out their steady state operation. Just as we did in the last lecture, we will take a few more problems. We will take 3 more problems and look at their steady state voltage gain, the current wave shapes, the losses in the converter, efficiency, and so on. What you see in this circuit here is an isolated converter. The power is transferred from the primary side to the secondary side, so that what is delivered, the V0 delivered from Vg is electrically isolated, and the source voltage is 24 volts. This is 24 volts, and the switch is operating with a duty ratio of 0.4 at a switching period of 20 microseconds, which corresponds to 50 kilohertz of switching. The switching is taking place at 50 kilohertz. The converter that we see here is a forward converter, isolated forward converter. So, during the time the switch is on, power is transferred from the primary to the secondary, and through this diode D1, it is delivered to the output inductor and to the output load. And whenever the switch goes off, the inductor current freewheels through the diode D2 and then feeds the output power V0 from the stored energy. So, in such a converter with a turns ratio of 1:2/3 between the primary and secondary, the ideal output voltage will be the input voltage 24 multiplied by the turns ratio, which is 2/3, and multiplied by the duty ratio, which is 0.4. So, this number is 8 and this is 16. 16 into 0.4 is 6.4 volts. So, ideally this power converter will deliver an output voltage of 6.4 volts if there are no losses in the converter. So, in this particular example, we would like to know what are the consequences of the various losses in the converter. We wish to know what is the output voltage V0 under the conditions that there are losses in the diodes, losses in the transistor, and losses in the magnetizing circuit. So, there are losses in the inductor also, losses in the primary winding, losses in the secondary winding. There are several losses in the converter. When these losses are taken into account, what happens to the ideal output voltage 6.4? Is it true or not? Definitely it is not true. There is going to be power loss in the converter, voltage loss in the various switches, and so V0 will certainly not be equal to the ideal value of 6.4 volts, and we would like to find out how this can be calculated. So, all the non-idealities are indicated here. The transistor drop is 0.4 volts. What we see, the MOSFET transistor has a voltage drop while it is conducting of 0.4 volts. The diodes which are on the secondary side of the transformer, they have a voltage drop of 0.8 volts during conduction. Then the primary winding of the transformer has a 30 milliohm of resistance. The secondary winding of the transformer has 60 milliohm of resistance, and the inductor itself has a resistance of 15 milliohms. All these are the non-idealities associated with the converter, and we had seen in the previous slide that the input voltage is 24 volts and the resistance is 1 ohm, switching period is 20 microsecond and duty ratio is 0.4. So, if we come back again to our, so this is 24 volts and duty ratio is 0.4. So, under this condition, how are we going to find out what is V naught? That is our current problem. So, in doing this, we know that V naught is found out by finding out the volt second balance on the inductor. So, we find out what is the voltage applied across the inductor over one cycle and equate it to the average value, we equate it to 0, and that is how we have been finding out the voltage gain, what will be the output voltage. Okay. So, we follow the same method, we try to now write the volt second balance for this particular converter. So, we can see that the inductor has a voltage of, go back to the previous slide, the inductor has on this side during the on time a voltage is 24 minus the device drop multiplied by the turns ratio minus the resistive drop on the primary minus the resistive drop on the secondary minus the diode drop on this side. Then on the output side we have V naught. So, if we write all these quantities, it is possible to write this volt second during the on time. The voltage across the inductor can be written as Vg minus the switch drop Vt minus primary current multiplied by RL. This is the voltage applied to the primary, that multiplied by N2 by N1 is the voltage on the secondary. The secondary side we have a diode voltage drop minus secondary current drop Is into Rs minus inductor resistance drop IL into RL on the left hand side of the inductor and minus V naught, which is the right hand side of the inductor. This voltage is applied for a duration of dTs. So, this is the voltage applied to the inductor, what you see on the square bracket, multiplied by dTs. Then during the off period, we have to add the voltage. So, that quantity is on the primary side, switch is off. So, nothing is coming from the primary side. The freewheeling starting from 0 minus 1 diode drop, the freewheeling diode, minus IL into RL minus V naught. So, this is the voltage across the inductor and this is for a duration of 1 minus dTs. So, adding both of these equal to 0. This is what we, this is the volt second balance equation. From this we should identify, we should isolate all the known quantities on one side and the unknown quantities related to V naught on the other side and find the relationship between V naught and Vg. So, this can be done by rewriting this equation. So, let me rewrite this equation as by expanding the terms Vg d N2 by N1 is the term on the first term, then transistor drop Vt d N2 by N1, right. So, we take all the other terms onto the right hand side and then minus Vd, all other terms are taken to the right hand side, that turns to be V naught plus ILRL plus ISRS into D plus IPRP into N2 by N1 into D So, these are all our quantities. The equation, all the quantities, like quantities relating to V naught have all been taken to the output side. So, this can be written as Vg d n2 by n1. This is the ideal gain. You please note how these terms are separated. The first term is the ideal gain. So, we write all the other quantities as a correction factor 1 minus Vt by Vg is the second term minus Vd divided by whatever is taken out is the ideal V naught. So, we will write it as ideal V naught. So, this is on one side, and the other side we will write this as again V naught multiplied by 1 plus this IL inductor current is the same as the output current. So, this can be written as RL by R, the load resistance, and similarly IS is the same as the inductor current. So, this will also be D times RS by R, the second next term, and this last term IP and IS are not equal to each other, but the primary current is related to the secondary current through the turns ratio. So, this IP can be written as again Rp N2 by N1 whole square divided by R multiplied by D, right, and that is the right hand side. So, effectively now we see that V naught is the ideal quantity with all the correction factors. The interesting point to see here is the way we have written it. When the non-idealities are 0, whatever is in this bracket will become 1. Similarly, whatever is in this bracket will become 1. So, all the non-idealities I have written in such a way that they will be a correction factor which will be 1 if all the ideal conditions true, and it will be different from 1 if the non-idealities exist. So, if you see this under ideal conditions, because these bracketed quantities are 1 each, V naught is same as Vg into d into n2 by n1. So, now we can write all these terms in terms of the ideal quantities. We can say that V naught is now Vg n2 by n1 into d. This is our ideal, and then we have, because we take all the terms to the one side, V naught is now related to the ideal gain, and then 1 minus Vt by Vg minus Vd by V naught ideal, and denominator has all these other terms 1 plus RL by R plus Rs into d by R plus Rp into n2 square by n1 square into d by R. So, you can see that all the numerator quantities of this correction factor has several minus terms, and the denominator has several plus terms which are contributing to the change in the output voltage. So, in our particular case, this ideal gain is 6.4, 24 volts multiplied by 2 by 3 into 0.4 duty ratio is 6.4, and all these other terms if I put in now 1 minus 0.4 by 24 Vt by Vg minus 0.8 by 6.4 ideal gain, and divided by 1 plus RL is given as 15 milliohm 0.15 by 1 plus Rs into D, which is 0.06 into 0.4 divided by 1 plus primary is resistance is 0.03 divided by 1, D is 0.4, N2 by N1 whole square is 2 by 3 whole square, which is 4 by 9. So, if all these numbers are put in, you can see that this is the correction factor, and this correction factor can be evaluated now, and once these numbers are evaluated, let me clear up this, we will find that V naught is 6.4 and these correction factors turn out to be 0.858 divided by 1.044, and this is 5.26 volts. So, on account of the various non-idealities, we find that the output voltage has reduced, has dropped by a certain voltage. So, that this is 5.26 divided by 5.26 instead of 6.4. Now, from this it is possible for us to find out what is P naught and what is Pi. So, P naught will be, the output voltage is now related to 5.26 square divided by 1 ohm, because our load is 1 ohm, 5.26 whole square. So, this is 27.67. So, this is just 5.26 square divided by 1 ohm, V square by R. And we also know that the efficiency as far as this particular process is concerned is the ratio of 5.26 divided by 6.4. So, if that is so, the input power is nothing but 27.67, which is the output power, divided by efficiency. If I divide by efficiency, this will be 5.26 and 6.4, and that will be 33.66. So, output power in this particular situation, output power is 27.67 watts, and input power, taking into account losses, what we have calculated is 33.66 watts. But then there is one particular loss which we have not accounted for. If we go back to the circuit, we have accounted for the losses in the switch, we have accounted for the losses in the diodes, in the transformer primary and secondary as conduction loss, and the inductor output L loss in the resistor of that. But we have not taken into account the loss that is taking place in the Zener diode, that is the magnetization loss. So, that is a separate loss which is taking place apart from these losses. So, let us find out what those losses are. Magnetization loss is related to the magnetization inductance of the transformer. In this particular case, that is given as Lm is 500 microhenry, and we know that on time is 0.4 and switching time is, switching period is 20 microsecond. So, the transformer is fed during the on time, transformer is supplied a voltage of 24 volts for a duration of 0.4 into 20 is 8 microsecond. So, this is the magnetization voltage, and during the off period, this energy goes through the zener and the transformer gets reset. So, we have seen that this is the Vz. Vz will be normally selected to be the same as this 24 volts. So, with this magnetization voltage, the transformer magnetization inductance Lm we will draw a current which will be linearly rising and then it will be linearly dropping. So, the magnetization energy that is picked up in the inductor is related to this magnetization current peak, and this current is whatever is the voltage applied to the transformer and the transformer magnetization inductance and the on time 8 micro. So, effectively the total magnetization current from this we can calculate, it will be 24 volts applied to the winding. Winding has a 500 microhenry and it is on for 8 microsecond. So, the total current will be 24 multiplied by 8 divided by 500, which is 0.384. So, this is the magnetization current and this is what is, we can probably draw it again, the transformer this is Ts, next cycle starts like that. So, this energy 3.384 amperes in every cycle is lost inside the zener. So, we can say that the magnetization loss Pm can be written as whatever is the energy in this Lm, 1/2 of Lm into Im square. This is the energy stored in the inductor, and if we switch at 50 kilohertz, every cycle so much of energy is lost. So, this would be the total magnetization loss, and this can be calculated as 1/2 Lm is 500 micro and Im is 0.384 whole square and frequency is 50 kilohertz, 50,000 Im square, right. So, this loss turns out to be, if you calculate that, it is 500 into 10 power minus 6 multiplied by 0.384 whole square multiplied by 50,000 divided by 2, which is 1.84 watts. Now, this is the additional loss compared to the what I had already calculated. So, the other P in without taking this into account was 33.66. So, I add all of them, 6 plus 4, 10. So, our P in is 34.5 watts and P out is 27.67 watts. So, from this we can say efficiency is 77.9%. Okay. So, what we had done is, first we did not worry about the magnetization loss, we wrote the volt second balance, because this magnetization is a shunt non-ideality that was separately calculated using the series non-idealities, which are the switches, diodes, resistors, etc. We evaluated what is the output voltage and we saw that was 5.26 volts starting from 24 volt here. Then after that we found out what are the losses in the various quantities. Then separately the magnetization loss was taken into account, that was calculated from here. So, with that we calculated the total input power, compared it with the total output power and wrote down what the overall efficiency is. Okay. If you now go back, we had seen that the magnetization loss itself is 1.84 watt. The this is magnetization, then P naught is 27.67 watts, and then P in minus magnetization loss we separately calculated, that was 33.66 watts. Then adding these two, we found out what is P in, and that is 35.50. 34, yeah, 0.50 watts, and from this the calculated efficiency is 77.9%. Efficiency calculated is 77.9%. Okay. So, we saw all the quantities that we had solved. V naught was 5.26 volts, then P in is 35.50 watt, P naught is 27.67 watts, and efficiency is 77.9%. So, this effectively is our total solution. We are interested in the gain that has been calculated, and we know what is the output power because we know the load, and what is the input power and what are the losses, input power minus output power, and what is the overall efficiency. Normally, this efficiency, this loss will appear as heat, and which has to be handled in the converter. So, let us look at another problem. This is a slightly different problem. It is on a non-isolated converter, non-isolated boost converter. It works from a source voltage of 20 volts, what you see here, and it is delivering an output voltage of 50 volts, and it operates with a duty ratio of 0.5, and the resistance is 50 ohm, load resistance is 50 ohm, so that the load current is 1 ampere. So, these are all the known quantities, and the inductor is given to be 20 microhenry. So, the first thing that we would like to know is this converter operating in CCM, continuous current mode, or discontinuous current mode? This is a boost converter. It is operating with a duty ratio of 0.5. If the in CCM, continuous current mode, output voltage is V in, input voltage, multiplied by 1 by 1 minus D, which is equal to 20 divided by 0.5, which is 40 volts. So, if the converter is operating in continuous current mode, the output voltage should be 40 volts. Okay. What we see here is an output voltage of 50 volts. V naught is 50 volts. So, it is possible now to evaluate whether the conduction mode is CCM or DCM. We know that V naught in DCM is always greater than V naught in CCM. So, clearly in this particular case, the output voltage is 50 volts and the continuous mode output voltage is 40 volts. So, this being higher than the continuous mode voltage, the converter is operating in CCM. That is the first conclusion that we can make. The operating point of the converter is such that the inductor current reaches 0 before the end of the cycle. The inductor current is not continuous. So, let us see how the inductor current will look like. In this particular case, we have output of 50 volts and 1 ampere, and input is 20 volts. So, if we neglect all the losses, P naught is 50 watts, Pi also will be 50 watts. If the input power is 50 watts and input voltage is 20 volts, we can say that the average input current will be 50 P naught divided by Vg, which is 2.5 amperes. So, it is possible that we can calculate the average current here is 2.5 amperes and the output voltage is 50 volts. The input power, assuming that there are no losses in the converter, all the components are ideal, the input power is same as output power, Pi and P naught are equal, and from that it is possible to find out what is the current drawn from the source. The average current is 2.5 amperes. The next thing that we would like to see is how the input current will look like. Okay. For example, the periodic input current wave shape is the next thing that we would like to see. We see that during the on time, we have seen that our 0.5 into Ts and this is Ts. During the on time, the current increases and reaches a peak value, and then because it is in discontinuous conduction, it reaches 0 current even before the end of the cycle, then current again increases from this. So, the average current of this is 2.5 amperes. The average current drawn from the source is 2.5 amperes. It has a peak current here, I peak, and it has 0 at this point, and this duration is something one we can find out. For example, in the boost converter, the ratio V naught by Vg is also written. If this is D and if this is D2, this ratio is given as D plus D2 divided by D2, and that is 50 by 20, which is 2.5. So, in this particular equation, D is known, all other quantities are known, it is possible to find out D2. So, if we evaluate D2 here, we will find that 0.5 plus D2 divided by D2 is equal to 2.5. So, we can write this as 0.5 plus D2 is equal to 2.5 D2, or 1.5 D2 is equal to 0.5, or we say D2 is 1 by 3. So, this is 1 by 2 and this is 1 by 3. So, for a fraction 1 by 2 of the cycle, the inductor current keeps increasing. Following that, for a fraction 1 by 3 of the cycle, inductor current keeps falling and eventually it reaches 0 at the end of 1/2 plus 1 by 3 of the duty ratio. So, this is the shape of the periodic current, and we would like to know what is this peak current, I peak. So, we know that the average current is 2.5, the shape has a triangular shape and then followed by a 0 region. So, this duration from here to here is D plus D2 Ts. So, if you take the average current, so we will draw that again. This is I peak, this is I average, which is 2.5 amperes, and this is 1 by 2, this is 1 by 3. So, if I take the average of the input current, I p into 1 by 2 plus 1 by 3, and because it is a triangle current, divided by 2 is the average, and that is equal to 2.5 amperes. So, you can say that IP 1 by 2 plus 1 by 3 can be written as 5 by 6 is equal to 2 into 2.5 is 5 amperes, or IP is equal to 6 amperes. So, the peak current here is 6 amperes. This duration is half the duty ratio, and this duration is 1/3 of the duty ratio. One cycle is Ts. So, from applying these principles, we have also found out the periodic current shape and what is the peak value and so on. The next thing that we would like to know is at what frequency is this converter operating. Periodic current wave shape we had seen already. It goes up to 6 and then so on. The average of that is 2.5 amperes. How is this 6 amperes obtained? It is the current reached during at the end of the on period. On period is T on, and the slope of the current during that time is Vg divided by L. So, Vg divided by L into T on, this is the peak current, and this is 6 amperes. Right. And this can be written as 20, the voltage in this particular example is 20 volts divided by 20 microhenry, inductor is 20 microhenry, into T on is 0.5 into Ts. This is equal to 6 amperes. So, here all quantities are known to us, and the only unknown quantity is Ts. So, we can write this as, take Ts to the other side, 20, 20. So, Ts is 6 by 0.5, 12 microsecond. So, from this equation we find out that the switching period is 12 microsecond, or the switching frequency is 1 by Ts, which will be 1 by 12 micro, and that is 83. 83.33 kilohertz. So, this is the switching period. The another quantity that we would like to know, switching frequency we have seen, switching period is 12 microsecond, and switching frequency is 83.3 kilohertz. So, the next thing that we would like to know is what is this conduction parameter, which is 2L by RTS. So, this in all continuous conduction and discontinuous conduction analysis depends on the parameter, conduction parameter of the converter, and that quantity is given as the ratio of 2L by RTS. In our case, 2 inductor is 20 micro divided by R is 50 ohm multiplied by Ts is 12 microsecond, and this quantity micro is gone, it is 40 by 40 1 by 50. So, conduction parameter K is 1 by 15, and this is the reason why this converter is right now in discontinuous conduction mode. Conduction parameter is very, very small. We have seen that if conduction parameter is more than this K critical in all these converters, they will be operating always in continuous conduction. In this particular case, we have found that the output is 50 volts which was given. So, from that we said that operating condition is in DCM. Then we found that the peak current in the switch is 6 amperes. Then we were able to find out the switching period is 12 microsecond. Conduction parameter is 1 by 15. So, this and D2, which is the freewheeling diode on time, is 1 by 3 times is the ratio. D2 TS is 1 by 3 times TS. So, by going through the principles of volt second balance and then the integration of the inductor voltage to find out the inductor current, and then from the inductor current finding out the average current, equating it for power balance, using all the basic principles, for this particular converter we were able to find out all the operating conditions. Let us see if we can move on to one more problem. Okay. This is another simple problem. Here this is also a non-isolated power converter. From the source voltage of Vg, we deliver a output voltage of V naught. Now, it consists of two switches, S and S bar. S is on during the on time, during this on time, and S bar is on during the off time, and it has totally 4 energy storage elements. Unlike the earlier ones that we had seen, it has L1, L2, C1, C2, and then finally the load which is delivering, which is receiving the power. This particular converter has a special name called SEPIC converter, that is single ended because one end is common, single ended primary inductor converter. So, this name SEPIC converter has come from this long name, single ended primary inductor. There is an inductor at the input side. This has an advantage because of the presence of this inductor, input current is continuous. So, in such a converter, again we might apply the same principles of volt second balance and find out the relationship between V1 to Vg and similarly V2 to Vg and so on. We have two inductors and we can apply the volt second balance on each one of them. For example, if we apply the volt second balance on L2, that will relate the V1 to V2. So, we can get a relationship between the voltage on capacitor C1 and voltage on capacitor C2 by applying the volt second balance on L2. Then if we apply the volt second balance in L1, we can find out the relationship between Vg and V1, how the source voltage is related to the capacitor voltage V1, capacitor 1. So, let us see if we can do this quantities. Volt second balance and V1 and V2 we will do on this. So, during the on time, when this switch is on, L2 is facing the voltage V1 with a minus sign. So, minus V1 into T on is the voltage across the inductor, and when this switch is open and S bar is closed, V2 is applied across L2, and that is plus V2 plus V2 into T off is equal to 0. and we can write this as, if you divide everywhere by Ts, it will be minus d times V1 plus 1 minus d times V2 is equal to 0, or we can say that V2 into 1 minus d divided by d is equal to V1, or V2 is equal to d by 1 minus d into V1. So, the conversion factor, ideal conversion factor for this gain, for this converter is d by 1 minus d, V naught by Vg is V2 V1. Now, we have to establish the relationship between Vg and V1. So, this is the volt second balance in L2. So, let us this was done, and we know that V2 is d by 1 minus d times V1. This is the first relationship. So, we can now do the volt second balance on the L1, and this is when the switch is on, Vg is what is applied across L1 with plus on this side and minus on this side. So, Vg into T on, right, is the voltage across the inductor, and then plus when this switch is off, the voltage across this inductor is Vg on one side, on the other side, because this is also closed now, it is V2 plus V1, Vg minus V2 plus V1 into T off is equal to 0. So, you can say that Vg into Ts is this first term is equal to V2 plus V1 into T off. V2 plus V1 is taken out to that side. So, that term you can write this as Vg is equal to V2 into 1 minus d plus V1 into 1 minus d. So, V2 itself is V1 times d by 1 minus d. So, this becomes V1 into d plus V1 into 1 minus d, that is equal to V1. So, what we find is the capacitor V1 voltage is the same as Vg, and capacitor V2 voltage is d by 1 minus d times V1, which is the same as Vg. So, this is our total volt second balance condition. So, if we wish to now see how the periodic current in L2 will be, L2 has a current, because L2 has the voltage V1 with a negative as shown here. When this switch is closed, minus V1 is applied to inductor during the on time. So, you will find that the inductor current will be falling down during that time, and then during the next time when S bar is on, inductor voltage will be rising. So, inductor voltage will fall during the on time for L2. This is L2. This is dTs 1 minus dTs. So, when the switch S is on, the capacitor V1 voltage, which is same as Vg, is applied reverse to L2. So, L2 current starts dropping, and during the time S bar is on, V2 voltage, which is plus on the top, is applied to the inductor. So, inductor current starts rising. Okay. This way. inductor current is in this polarity. So, when the switch is on, inductor current is rising in the polarity shown here with arrow, and when this switch is off, it is going in the other, it is in this polarity it will be falling. Let me draw that correctly. This is always fine. So, the inductor current now I will show in this polarity, in this direction. This is the direction of the current, and it will go and charge this. So, in that direction, negative voltage is supplied to L2. L2 current will be rising in the direction that is shown here, rising, and during the next interval it will be falling during the time it is next cycle goes on. So, this will be the I2 current, and this is I2 average current, the average current in the inductor. So, the voltage across the inductor L2 has Vg on one side and V0 on the other side. So, let us see the next. Periodic current in L2 has a rising time which is Vg by L, and a falling time which is V0 by L2. Now, if the load is decreased in the converter, this current will keep dropping and eventually it will reach discontinuous conduction. As you move, as the current keeps coming down, eventually the converter go into discontinuous conduction mode. So, in the discontinuous conduction mode or in the border between the continuous conduction and discontinuous conduction, you will find that the rise in the inductor current and fall in the inductor current Vg by L2 and V0 by L2, they both will be finally it will reach 0 condition, and the output average current, the inductor current during S bar only is contributing to average current. If you call this as D and this as 1 minus D, then the peak current I peak into 1 by 2 into D2 or 1 minus D, if it is in the border 1 minus D, this will be equal to the output current I0, output current which is going into this I0. So, from this it is possible to find out, let us see how this particular quantity is carried out. The peak current this I peak can be calculated to be Vg by L2 into dTs. So, this is I peak, and I0 which is output current, which is I peak by 2 into 1 minus D is equal to V0 by R. This is I0 which is V0 by R. So, from these quantities, see, it is possible to say that on the border of continuous and discontinuous conduction, the output current V0 by R equal to IP by 2 into 1 minus D, So, if I now substitute IP from here, you will find that Vg by L2 dTs divided by 2 into 1 minus d is equal to V naught by R. And V naught itself is Vg into d by 1 minus d R. So, from these two, by combining, by substituting IP, we have put that d will cancel with that, Vg will cancel, and we find that 2L2 by Rts is equal to 1 minus d whole square. So, this is the condition for the operation to be on the border between CCM and DCM. We can say that the condition 2L2 by RTS, this is called the conduction parameters in all these converters, this K is equal to 1 minus d whole square. So, if this is true, then we will find that operation is on the border between continuous conduction and discontinuous conduction. And if this 2L2 by RTS is greater than 1 minus d whole square, then conduction is continuous. If it is less than 1 minus d whole square, conduction is discontinuous. If it is equal to 1 minus d whole square, then that is the border case. So, in SEPIC converter also, just like flyback converter, this border between continuous and discontinuous conduction equation is identical. This relationship between conduction parameter and duty ratio is identical in SEPIC converter as the flyback converter. So, with this set of problems, we have also now demonstrated to ourselves that using the volt second balance, finding out the voltage across the inductors, current through the inductors, average currents, and then the ideal voltage to voltage gain and ideal current to current gain. We know that ideally when there are no losses, forward voltage gain is same as reverse current gain, and we have also seen that it is possible to incorporate the losses in the converter and find out how the voltage gain changes, how the converter losses can be represented through the efficiency of the converter, and so on. So, in the following lectures, we will get on to develop dynamic models for these converters. We will stop with this on the steady state performance on the converters. In the coming lectures, we will try to understand the dynamic operation of the converter and the mathematical model, and how to analyze the converter during the transients.